Hello and welcome to General Linear Models 2 Electric Boogaloo. You might think that's a bit of a weird session title, and you're kind of right. And you might have seen that Electric Boogaloo thing on social media. It's often talked about when there's a sort of sequel to something. So, for instance, in the UK, like Lockdown 2. And it comes from a film in the 1980s about breakdancing, and they made a really unnecessary sequel, which was called Breaking 2 Electric Boogaloo. And I guess why it was in my mind when I was thinking about this session was we talked about general linear models, we talked about ANOVA, and we started to go on and look at ANCOVA and MANOVA. And I'd been watching It's Always Sunny in Philadelphia. And in one of the episodes, they invent a homemade board game called Chardee McDennis. And in a later series, they play this game again. They have a follow up. So the episode's called Chardee McDennis 2 Electric Boogaloo. And in that episode, it got me thinking about their board game having different levels. And in this session and its partner, we are going to start looking at data analysis at multiple levels. So throughout this session, we're going to be thinking about single level analysis, and then in the partner session, we can go on to explore to look at multi-level analyses. So to give you an overview of this presentation, we're going to be talking about how we model categorical outcomes, and again we can do this through general linear modeling. And the main ones that we're going to talk about are chi-square analyses and log linear analyses, before moving on in our paired second session to look at multi-level linear models. Previously, in our first session on general linear model, we looked at categorical predictor variables, such as biological sex, and we considered only continuous outcome variables. And this would be, for instance, the score on the hockey shooting task. But what happens if we want to predict into which category an observation will fall? So, for instance, going back to our hockey shooting task, if we had only given the participants one trial, i.e. one shot at the goal, and we wanted to record whether it was a hit or a miss, how can we actually predict that based on, say, for instance, a categorical predictor like biological sex? And certainly in terms of applied psychology, this type of data modelling is really important and really, really valuable, both in terms of its contribution to society, but also in terms of being monetised. So for instance, if you want to try and predict which political party someone will vote for, whether you're going to predict whether a sports team are going to win, lose or draw, or whether or not a health outcome is likely to be positive or negative. So what can we do as researchers? We can think about associations between categorical variables. We can try to predict categorical outcomes, goals versus misses, yeses versus nos from categorical predictors. Or indeed we can try to predict categorical outcomes from both categorical and continuous predictors. So, one thing to bear in mind is that if you're using categorical variables, we try to use our frequencies, observed values of data, as our descriptive statistics rather than means. So for instance, if we take a hypothetical research study where an attempt has been made to increase pro-social behaviour, in this case whether or not people will pick up pieces of litter. So let's say that our staff and students at a university campus, or teachers and pupils at a school, are given separate interventions. One group are rewarded for collecting litter, i.e. they get an extra 5 minutes added onto their break time, or another group are actually punished if they don't pick up their litter, and that is they lose 5 minutes of their break time. And then we set up a scenario where participants have the opportunity to remove a piece of litter. This is maybe staged by the experimenter, and we record the number of participants who either pick up the litter or do not, and we can associate that with whether or not they were in the reward group or the punishment group. We can plot out the numbers of participants in each of these cells of a table. So for instance, here we have 86 participants who were in the reward intervention who did pick up the litter, and 73 who did not. We have 64 participants who picked up the litter after receiving a punishment intervention and 77 who did not. So across our sample, we have 150 participants who did pick up litter and 150 who did not. That's a quirk. Those numbers don't have to be equal. We maybe have 159 people that attended or took part in the reward intervention conditions and 141 who took part in the punishment. Overall, we had 300 participants. This is technically known as a contingency table, and for instance, if you're using a package like SPSS, you can choose how these are formatted. For instance, you may wish to display the row totals, the column totals, the observed frequencies, or you may even choose to actually have the expected frequencies within the same cells. And I'll talk more about expected frequencies as we move on. We could have these expressed as percentages, and again, depending on the data that you're dealing with and the audience you're trying to communicate with, it may be more or less appropriate to use the actual frequencies, or you may wish to convert to percentages. The first test we're going to talk about is known as the Pearson's chi-square test, and please bear in mind that it is pronounced like a kicking k. It's not a ch. It's not chai, as in like chai ovna. It's Kai, also like the son of Wayne and Colleen. And one thing that might seem like nitpicking, but is to actually try and use the appropriate symbol. If you're using a Microsoft package, you can go to the Insert tab on the ribbon and put in a symbol. It's a lowercase chi, or indeed you could copy and paste that symbol from a different source. Using an X is actually a different statistic, so please take the time to actually either insert or copy and paste the chi-square symbol. And what the chi-square allows us to do is to test, for example, in our previous example, the likelihood of picking up litter, and does this relate to the type of intervention that was carried out. This is essentially a test of what we have observed, an outcome, versus what we would have expected at chance. In another way, you could think, does the model of the data that we attempt to build, for that matter, our contingency table of predictors and outcomes, better fit our data than no model at all, or a model that's only composed of sort of error terms? There's a mathematical formula that underlies the chi-square, and this is similar to the mathematical equation that determines the sums of squares errors in a linear model. So for instance, when you're looking at your SPSS output, when you do something like an ANOVA or an ANCOVA, within the output table you will see this term, sums of squares, and that would be in a linear model, and it's only a very, very different, ever so slightly different formula that is used when variables are categorical. What we're basically doing is dividing the differences between our observed data and the data that would be predicted by our model by the model scores. So this essentially standardizes the deviation of each observation. And when we add up these standardized deviations together, this is what basically gives us chi-square statistics. The chi-square statistic represents the sum of the differences squared of observed and expected frequencies, and the squaring becomes important so that we don't end up with negative or zero values. If we remember, if we square a negative number, it gives us a positive. Because if we think back to our material on linear modelling, you're trying to plant a model that's going to estimate data, and sometimes your model is going to overestimate a value and sometimes it's going to underestimate a value, i.e. positive and negative differences from the estimate. So if we just added them all up in a perfect model, they'll come out as 0, because then you're basically saying there's no difference between your model and the observed data. So we need to square the differences so that we get rid of that sort of directionality about whether the difference between your observed and expected data is positive or negative. So if we go back to our litter picking example, we've got 300 participants here, and if we had equal number of participants in our reward and punishment groups, we could just simply divide that 300 across the 4 cells, and that would mean at chance, completely random, no effect of our intervention, we would expect frequencies of 75. 4 times 75 gives us 300. But we know that we've got 159 participants in the reward condition and 141 in the punishment condition, so there's a difference there. We have to factor that in. And similarly, there's different numbers of participants who did or did not pick up the litter. So what we do when we're conducting a chi-square test is we adjust for these uneven numbers, and we calculate our expected frequencies using the row totals, i.e. adding up the number of observations in cell 1 and cell 2 to give us value A, or indeed adding up the numbers in cell 3 and cell 4 to give us value B. And we also use the column totals associated with each cell. So we use the total that was obtained by adding up the leftmost 2 cells in the table, and the total obtained by adding up the rightmost 2 cells in the table. So let's look through this in terms of arithmetic, and the reasons for doing this will become clear later. We have the 86 participants who did pick up litter after reward, and 64 participants who picked up litter after punishment. This gives us a row total of 150. We have 73 participants who didn't pick up litter after the reward condition, and 77 who didn't pick up litter after the punishment intervention. So that we have another row total there of 150. The number of participants in the reward condition is 159. That's the 86 yeses and 73 noes added together. And we have a punishment total group of 141, adding up the 64 who did pick up litter after punishment and the 77 who did not. So to work out the expected frequency of the reward times yes cell, so those who did pick up litter after being rewarded, we take the row total of 150, we multiply it by the column total of 159, and divide it by our total number of observations. Following this arithmetic through, we end up with an expected frequency of 79.5. And if we repeat this process of taking a row total, a column total, multiply, divide by the overall number of observations, we see that we get our expected frequencies. So that's a row total, a column total, and the overall number of observations. They all act together to give us these expected frequencies. What we then go on to do with the chi-square formula is we take these expected frequencies that we've generated and we plug them into the chi-square formula. So we had 86 people who were in the reward group and who did pick up litter. That's our observed value. We'd worked out that we could have expected 79.5 people in this cell based on no information other than the row and column and total participant data. We square it to get rid of any negative number, and we divide it by the expected number of cells to standardize that sort of deviance. And we repeat this for all other cells in our contingency table. We take the observed value, we subtract its particular expected value, square that difference, and then divide by the expected frequency. And we repeat this for all the cells in our contingency table. We work out the chi-square value by adding up the product of these sums. So if we followed this through using our litter example, using our observed and expected frequencies, we would end up with a chi-square value of 2.26. If you're doing chi-square by hand, as we are in this example, you would then look up what's called a critical value table. And if your value of chi-square is greater than that in the critical value table, you have a significant result. So our litter example, we worked it all the way through. We got a chi-square of 2.26. We then calculate our degrees of freedom, which is the number of rows containing observed data in our table, multiplied by the number of columns that contained observed data. So in our litter example, we had 2 rows which contained observations. We take away 1. We had 2 columns which contained observed data. We take away 1 and multiply it, 1 times 1 being 1. So the degrees of freedom for every 2 by 2 contingency table is always 1. The critical value of chi-square at the 0.05 level is 3.84. So with our actual chi-square value of 2.26, we haven't reached the critical value. 2.26 is a smaller number than 3.84. Therefore, we do not have a significant association between the variables. We cannot accept that we have an association at the 0.05 level. So typically, larger chi-square values means greater differences between the observed values and those which would be predicted without a model, just completely at chance, no impact of your manipulation. So larger chi-squares lead to significant results, i.e. significant associations between your variables. So the chi-square statistic is underpinned or overlaid on a distribution that approximates a chi-square distribution. And when you've got a really large sample, the better this approximation becomes, the closer it gets to the proper chi-square distribution. To the point where you actually don't need to worry about the fact that the statistic isn't actually perfectly matching onto the distribution. If you've got a small sample, or indeed you're dividing a relatively small sample across lots and lots of cells in a contingency table, i.e. you've got lots of levels of your predictors or lots of levels of your outcome, this becomes really problematic. So in the past you might have been told to be careful or to watch out for expected frequencies of less than 5 in each cell, and people maybe didn't actually explain to you why that is, and it's because when you're dealing with small amounts of data like that, the fact that the chi-square statistic doesn't perfectly match the distribution, it becomes a big problem. And if we go back to the arithmetic that we use to actually generate the chi-square, larger samples, fewer cells in the contingency tables automatically will increase your expected frequencies. Fisher's exact test is something that you might see referred to either in the literature or when you're using a statistical package like SPSS. And what Fisher's exact test does is it computes the exact probability of the chi-square statistic in small samples. This is normally when you're using one of those sort of 2 by 2 tables like we had in the litter example. So 2 levels of the intervention, reward and punishment, 2 possible outcomes. Did they pick up the litter? Did they not pick up the litter? You can, technically speaking, use Fisher's exact test on larger samples and larger contingency tables, but there really isn't any point because, as I said earlier, the larger the sample, the better the approximation of the distribution. So you're as well sticking to the generic sort of Pearson's chi-square statistic with a big sample. There's another term that you might come across when you're reading about chi-square or even when you're interpreting statistical output or using the command menu using something like SPSS, and that's called a Yates correction. It has nothing to do with wine lodges. When you have a 2 by 2 contingency table, Pearson's chi-square tends to be a wee bit lenient, so the significance values that are returned tend to be a wee bit too small, so there's a likelihood of making a type 1 error where you claim that you've got an association between your variables that isn't actually real. What Yates's correction does is it takes away 0.5 from the absolute value of the difference between the observed and the expected frequencies. And I've gone back to the litter example data and reproduced this data manually to show what a Yates's correction would do. So we had, for instance, in our reward intervention and people who did pick up litter, we had 86 participants who fit those criteria. Our expected frequency was 79.5. We substitute the 79.5 from the 86, but applying Yates correction, after we've done this, we subtract an additional 0.5 before squaring that difference. And we repeat that for all cells in the model. This will actually lead to a slight adjustment of the chi-square statistic. So if you remember, or you revisit the slides from a few pages ago, our original chi-square was 2.26. Applying the Yates's correction in this instance actually gives a slightly larger chi-square value, which is 2.28, but our 2.28 is still below the critical value of 3.84. Therefore, we do not have a significant value. Our p value is still greater than 0.05. There is no association with the variables, or between the variables and the outcome. So far you might be struggling to think of this as a linear model, and that's understandable, but we can conceptualize chi-square as a linear model. And if you access the Andy Field textbook, there is a sort of very mathematical depiction of how chi-square is in effect a form of linear model. And if we think way back to the very first couple of slides of our first session on GLM, what is a linear model? It is basically a relationship between an outcome and a predictor. And in effect, that's what chi-square does, but this time dealing with categorical outcomes. So what we can do is we can code the categories of each variable using dummy coding, and again this is something that crops up in linear modelling, particularly around regression. And the equation of our linear model would represent the outcome as a function of your model plus an error term. So we put in our categorical variables as predictors into the model, we use our observed values as the outcomes, and we can use a sort of log transformation of these values. The chi-square is then going to test us whether or not the variables are independent or associated. The model is basically the expected frequencies, and the residuals represent the differences between the observed and the expected values. So essentially the chi-square is a linear model with beta values, and again if you go back and think about regression, or you think about the sort of mathematics that underpin a linear model, the beta values are really important. The chi-square is essentially a linear model with beta values that tell us the differences in frequencies across our variables. As I said, I don't want to represent this mathematically in this presentation, but something like the Andy Field SPSS statistics book, or books by Tabachnik and Fidel have very, very detailed mathematical representations for those of you who are interested in that method of understanding the material. A slightly different but associated concept is this one of log linear analysis. Log linear analysis is a very, very useful statistic, or a very, very useful approach to data analysis. And this is used to analyse more complex contingency tables in which there are sort of 3 or more variables. So for instance, going back to our litter example, if we have the same intervention of reward or punishment, and the same levels of outcome, did the individual pick up the litter, yes or no? What if we wanted to look at whether or not it was teachers or pupils? Does that have an effect on our behaviour? You can't really do that with a chi-square, so you would tend to use a log linear analysis to interpret that type of multiple predictor model of a categorical outcome. What we're doing with log linear analysis a little bit differently than we did with the out-and-out chi-square is that we we translate our categorical variables using log transformation, using the natural log ln as a function. Hence the term log linear. We're using log transformed values, but we're still fitting a linear model to our data. And the nice thing about log linear analysis is that you can input any number of predictors and any number of interactions between the predictors. But as a caveat at this stage, what you choose as your predictors should be determined during sort of research development stage. You should have either a theoretical or an empirical reason for selecting those predictors, rather than simply ending up with a massive data set and deciding to go on a bit of a fishing trip to see if you can build some sort of meaningful model of your data. And one thing that's really important with log linear analysis, as it is with regression analysis and other types of multi-level data, is that you're trying to fit the simplest model to the data without losing any of the predictive power. So more complex models are not actually better models. What you should actually be aiming for is the simplest model that generates the most amount of power. And I'll come back to this shortly. The way we do this is in a process of backwards elimination. So you start by basically saturating the model. You put sort of everything in that you'd sort of a priori identified as empirically or theoretically relevant to your outcome. And then you start to take away the most complicated terms. So you start with the full model, you subtract the most complicated, you start with a full model and you estimate it and you get all your parameters and measures. You then take away the most complicated term and redefine the model, and then you test those two models relative to one another to see if there's any change from the most complicated model to the next most complicated. And if the simpler model fits the data equally well, we should abandon the most complicated one. This is a concept known as parsimony, and sometimes in the literature you'll come across the test a parsimonious explanation, and that is essentially trying to apply the simplest model or the simplest solution to your data. Another way to think about this is that if you assume that the removed term did not significantly impact the ability of the model to predict the outcome. So you've started with the most complicated model, you've got all your model estimates and measures related to it. You then rebuild the model, having extracted the most complicated term. If that removed term hasn't significantly impacted the model, you can say that factor isn't having a significant effect. And we take a hierarchical approach to term removal. So you start always with the highest order interaction term first. So for instance, using our litter example, if we'd looked at intervention type, outcome and role, i.e. were they in the reward or punishment group, did they pick it up, yes or no, were they a teacher or a pupil, we would start with the fullest model and then we would remove that three-way interaction. So we would build the full model and collate our data. We would remove the three-way interaction, rebuild the model and compare those two models that we've generated. And you essentially work downwards in this backwards elimination style until you actually weaken the model. Now that might happen at the very first step, in which case you've got a significant three-way interaction and you have to stick to that full model. But it might be that you take out the three-way interaction and there's no significant change in your ability of the model to predict the outcome, in which case you would then work through the two-way interactions. And maybe then you do start to notice that taking out a two-way interaction significantly impacts your model and its ability to predict your data. And that's where we would stop. Essentially, when the model starts to change is where you stop. Alternatively, it's perfectly feasible that you might end up removing all the two-way interactions and end up only looking at main effects within your model. It changes on a case-by-case data. It changes case by case based on the data that you have. The means by which we compare the full model to the reduced model is using something called a likelihood ratio, which is sometimes represented as a chi-square. So, we started with chi-square for a very good reason in this session. So if the new model significantly changes the likelihood ratio statistic, then when you removed that term to reduce the model, what it has done is it's significantly affected the ability of the model to fit the data, and therefore the term that you have removed is actually significant. So using our litter example, if we had built our full model, then dropped out the three-way interaction, rebuilt the model, retested it, and showed that we had changed these likelihood ratios, we would simply stop, because this means that the three-way interaction is significant, and a three-way interaction overrules or sort of supersedes any two-way interactions or main effects. They're sort of subsumed within the three-way interaction. And going back to thinking about things like analysis of variance, we're often taught to look at the output table in terms of the main effects. So, each predictor in that linear model on its own, and then we work our way down to the interaction term. And often that's how we're sort of taught to report analysis of variance as well. However, that's actually a backwards approach. What we should be doing with analysis of variance is actually going straight to the interaction term, because if the interaction term is significant, or if the highest order interaction term is significant, then in effect none of the other effects actually matter, because the most complicated interaction term, if it's significant, will overrule or override any of the subordinate terms. If we build our model and we drop out the three-way and nothing happens in terms of the ability of the model to fit the data, then yeah, we start working our way through the two-way interactions in turn, and we make decisions at that stage. And again, if dropping those out, comparing those to the full model, then again we start to look at our main effects. And if dropping out absolutely everything doesn't make a difference, then essentially we've got no significant main effects. None of our predictors are related to our outcome. So the model, any model that we build, isn't doing a good enough job. In terms of our practical sessions, we're not going to conduct chi-square or log linear analyses. And in all seriousness, one of the reasons that I wanted to get a bit arithmetical and mathematic with the chi-square example from the 2x2 litter example is that for a 2x2 chi-square, you're actually maybe better carrying this out by hand or with a calculator, rather than building an actual SPSS file and fiddling about. In SPSS, there's sort of two ways to do the chi-square. One is through Analyze menu, Descriptives and Crosstabs. The other is through the Analyze menu, Non-Parametrics Tests, Legacy Dialogues and chi-square. SPSS is notoriously fidgety to do chi-square. So, if you've got access to drawing your own contingency table, if you're comfortable following the formulae and the step-by-step instructions earlier in these slides, you might be just as quick to actually perform the chi-square by hand. Obviously, you'll need to have access to a chi-square critical value table so that you can figure out whether your obtained chi-square reaches that critical value level. You can look that up on Google, or you can look it up in the back of many statistical textbooks, but a chi-square with degrees of freedom 1, i.e. a 2x2 contingency table, the critical value for 0.05 significance is always 3.84. So that's something to bear in mind. If you are interested in actually conducting these tests using something like SPSS, then you could follow the instructions in the field textbook and the associated practical exercises and data sets. In future years, when it comes to your own empirical work, when it comes to your own research, and you're considering either chi-square or log linear analysis, please either discuss this with your supervisor or come back and speak to a member of our analytical methods team.